Hello and welcome to The Sleepy Scientist. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. This video is made just for you. Tonight, we'll be gently gliding through the cosmos to uncover one of the strangest truths in physics: why light, of all things, has a speed limit. But before we begin, I'd love to know, where in the world are you listening from, and what time is it where you are right now? Are you winding down under city lights, or nestled somewhere quiet and dark, perhaps with a cup of something warm? If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these soft starlit journeys for you. Now, I do hope this video isn't too interesting though. If it does accidentally keep you awake, at least you'll come away knowing a bit more about how our universe works. Not such a bad trade really, so settle in, close your eyes, if you like, and let's take a slow, thoughtful wander through the story of light, and why it's in such a hurry to get anywhere at all. Light is one of those things we all think we understand until we actually try to explain it. You flip a switch, and there it is. It fills the room, lets you see your cat's judgmental stare, and makes your phone screen glow long after you swore you'd put it down. But what is it really? Is it a wave, a particle, a ghost, a cosmic courier with a very strict delivery schedule? The short answer is yes, and also sort of. Let's take a nice slow wander through what light actually is. Because before we can understand why it has a speed limit, we first need to understand what's actually doing the speeding. First, let's talk about photons. They're the tiny packets that make up light. Imagine them as little messengers zooming through the void at the fastest speed allowed by the universe. But these messengers are strange. They're not particles in the traditional sense like marbles or peas. They don't have mass, they don't rest, and they definitely don't follow the usual rules. Now, here's where it gets fun. Photons are also waves, but not waves like ocean waves or wavy hair. They're electromagnetic waves, vibrations of electric and magnetic fields that oscillate at right angles to each other and to the direction they're moving. Yes, it sounds like a physics yoga class, but the mental image is quite elegant. Two fields dancing through space together, locked in a perfect rhythm. These waves don't need a medium to travel through. That's important. Most waves, sound waves, water waves, even the wave you give your neighbor from across the fence, need something to move through. Sound needs air, water waves need well water, but light just goes. It travels through the vacuum of space without a problem. That's why we can see the sun, which is over 90 million miles away. Its light has traveled through the emptiness of space to reach us without a single rest stop. And it doesn't just come in one flavor. The light we can see, what we call visible light, is only a tiny part of the electromagnetic spectrum. Imagine a piano that stretches for miles. Visible light is just a handful of keys in the middle. On one end of the spectrum we've got radio waves, long lazy undulations that can stretch for miles. On the other end we've got gamma rays, sharp high-energy spikes that can pass through almost anything and are usually found in the company of exploding stars and nuclear reactions. In between you've got microwaves, infrared, which your TV remote uses, ultraviolet, which gives you sunburns, and X-rays, which can see through your bones, but somehow never find your missing socks. But despite all these differences, all these forms of light move at the same speed in a vacuum, roughly 299,792,458 meters per second. That's just under 300,000 kilometers every single second. A number so big it feels like nonsense. It's like saying, how fast is that? And the universe replies, yes. To put it in bedtime terms, if light were a runner, it could jog around the entire Earth more than 7 times in a single second. Not bad for something with no legs. But here's something else to keep in mind. Light doesn't always go that fast. In a vacuum it's got a clear track and no traffic. But when it passes through something like water, glass, or even diamond, it slows down. Not because it's tired, but because it's interacting with the material's atoms. It's a bit like walking through a crowded room. You're still heading in the same direction, but there's a lot more bumping and weaving to do. That slowing down is what causes refraction, the bending of light. When it moves from one material into another, that's why a straw looks bent in a glass of water, or why a diamond sparkles so brilliantly. It's all about how light's journey gets delayed, rerouted, and scattered. But here's the twist. Even though light slows down in these materials, Individual photons still travel at the same speed between atomic interactions. They're just taking a more complicated path, like someone trying to speedwalk through a dance floor full of enthusiastic uncles at a wedding. Now let's talk for a moment about color. When we look at a rainbow or a prism or the weird oil slick in a puddle, what we're seeing is light split into its various wavelengths. Each color of visible light has a different wavelength, is long and lazy. Violet is short and twitchy, but all of them are still photons. Still electromagnetic waves, just vibrating at different frequencies. Your eyes have special cells, called cones, that are tuned to specific ranges of those wavelengths. That's how you see color. It's not that the apple is red, it's that it's reflecting the wavelength we interpret as red while absorbing the rest. So in a way, color is just your brain's best guess, based on which vibrations make it to your retinas. And as if all this weren't already wonderfully strange, light also has no rest mass. That means, unlike you or me, or your slightly judgmental cat, it doesn't need energy to move. It always moves. It has no choice. If a photon were to stop, it wouldn't just be taking a break, it would cease to exist. It's motion or nothing. All are gone. And that's not just poetic, it's physics. So we've got these massless packets of energy that behave like both waves and particles, that travel at a universal speed, that can interact with atoms, bend around corners, and bounce off surfaces, all while delivering the very experience of sight and color to conscious brains like ours. And that's just scratching the surface. But for tonight, let's hold on to this image. Light as a restless traveler made of no substance but energy, never pausing, never sleeping, always tracing the outlines of everything we know. It shows us the stars, the faces we love, the pages of our favorite books, and it does all this while obeying one of the most curious rules in the universe, a speed it will never exceed and never fall below. Light isn't just what helps us see, it's how the universe whispers its story into our eyes. Let's take a gentle step back in time, long before satellites and lasers, before physicists had high-tech toys to measure the universe's secrets. Imagine a world lit only by fire and stars, where understanding something as elusive as light speed was not just difficult, it seemed almost absurd. For most of human history, people believed that light moved instantaneously. It was just there. You lit a candle and the room lit up, the sun rose and the world turned golden. No waiting, no delay. It seemed obvious. Why would anyone think otherwise? Even the ancient Greek philosopher Empedocles, one of the few to suggest that light might have a finite speed, wasn't taken very seriously. Aristotle, whose opinions had the unfortunate habit of sticking around for centuries, thought light was instantaneous, and that was that case closed, curiosity shelved. But then came Galileo, and Galileo was not one to accept things just because someone important said so. He liked to poke things, drop them off towers, and point telescopes at moons. And around the year 1638 he tried to measure the speed of light in what might be the most adorably optimistic experiment in history. The idea was simple. Galileo and his assistant each took a lantern, covered it, and stood on hilltops about a mile apart. Galileo would uncover his lantern, and as soon as his assistant saw the light, he would uncover his in return. Then Galileo would measure the time between sending the signal and seeing the return flash. Now, even under the best of circumstances, this experiment was ambitious. The human reaction time alone is about 1/4 of a second, while light meanwhile takes less than a 10,000th of a second to travel a mile. It's like trying to measure the speed of a bullet with a sundial. Still, you've got to admire the effort. Galileo, unsurprisingly, concluded that if light did have a finite speed, it was far too fast for him to measure, which was true, but at least the question had been asked. Fast forward a few decades to a Danish astronomer named Ole Rachmer, who, in 1676, would accidentally stumble upon the answer by watching something quite far away, the moons of Jupiter. Rachmer was tracking the orbit of Io, one of Jupiter's many moons, which zips around the gas giant like cosmic clockwork, and by carefully observing when Io disappeared behind Jupiter and when it reappeared, he noticed something odd. The timings weren't always the same. Sometimes Io appeared a little late, other times it was a bit early. At first glance this might seem like bad timing, but Rachmer had a brilliant thought. What if it wasn't Io that was being inconsistent, but us? What if the delay was caused by the fact that Earth was sometimes farther away from Jupiter and the light from Io had farther to travel? And just like that, the idea of light having a measurable speed began to take real scientific shape. From these timing discrepancies, Rachmer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit, a distance that represents the foundation of our understanding of light's cosmic speed limit. We now understand it to be roughly 186 million miles, quite remarkable when you consider he lacked precise measurements or sophisticated timepieces. His calculation wasn't flawless, but it was groundbreaking, demonstrating to humanity that light requires time to travel. Not much perhaps, but sufficient to be significant. Later, in the early 19th century, a physicist named Hippolyte Fizeau chose to attempt something more terrestrial. His approach utilized a light beam, a spinning cogwheel, and a mirror positioned miles distant. The process worked like this. The light beam passed through spaces between the wheel's teeth, journeyed to the remote mirror, and reflected back. When the wheel rotated slowly, the returning light would slip through the identical gap and remain visible. However, if the wheel spun rapidly, the returning light would strike a tooth rather than a space and become blocked. By modifying the wheel's rotation speed, Fizeau could determine the precise moment when the light beam vanished completely, indicating it had just enough time to reach the mirror and return while the wheel turned half a tooth's distance. Using the established distance and wheel velocity, he determined light speed at approximately 193,000 miles per second. Remarkably close to today's accepted value, especially considering he worked with mirrors, mechanisms, and considerable ingenuity. Subsequently, another researcher named Léon Foucault enhanced the method by employing rotating mirrors rather than toothed wheels. Substantially improving accuracy, he demonstrated not merely that light possesses finite speed, but that it actually travels more slowly through water than air. A vital discovery showing light interacts with matter in ways that influence its velocity. Perhaps the most celebrated figure in this saga is Albert Michelson. During the late 1800s, Michelson refined Foucault's approach and perfected it to unprecedented precision. He employed lengthy tunnels, meticulously positioned mirrors, and extraordinarily accurate timing to achieve results that amazed the scientific community. His dedication earned him the Nobel Prize in Physics in 1907, making him America's first recipient of this distinction, not an insignificant achievement for someone pursuing light beams with reflective surfaces. Today we possess superior instruments, lasers, atomic chronometers, satellites. We've actually defined the meter itself using light speed. Since 1983, the meter has been officially established as the distance light covers. In 1/299th, 792,458th of a second, in essence, we've reversed the calculation. We no longer measure light's speed, but employ it as our foundation for measuring everything else. Yet it all began with individuals observing moons, rotating wheels, and questioning whether the universe might be more gradual than appearances suggest. Perhaps that's the subtle elegance of it all. Light speed isn't merely a figure, but a narrative, a chronicle of inquisitive intellects, imperfect instruments, and graceful determination. An account spanning centuries told from mountain peaks, observatories, and distant trajectories. Evidence that even the universe's swiftest phenomenon couldn't escape human curiosity. Now that we've encountered our swift photon companion and traced the extended fascinating quest to measure its pace, let's pose the question that truly haunts physicists. Why doesn't light simply move faster? After all, it appears somewhat arbitrary. Why 299,792,458 meters per second? Why not a convenient 300 million or 500 million or simply infinite? Why must light, this ethereal, massless bundle of energy, obey a cosmic velocity restriction? To comprehend this, we must venture into one of physics' most elegant and mind-expanding domains, electromagnetism. Specifically, we'll discuss James Clerk Maxwell. During the 1860s, Maxwell gathered everything scientists understood about electricity and magnetism. Consider Benjamin Franklin's lightning conductors and Michael Faraday's coils and magnets, and transformed it into four magnificent mathematical expressions known rather unimaginatively as Maxwell's equations. They describe how electric and magnetic fields interact, transform, and propagate. You needn't concern yourself with the actual mathematics. Nobody will test you later. But here's the fascinating aspect. When Maxwell unified these equations, he uncovered something extraordinary. They predicted a wave type, an electromagnetic wave that would naturally arise whenever electric and magnetic fields oscillated precisely. This wave would invariably travel at a specific velocity. When he performed the calculations incorporating known values for electric and magnetic constants, he obtained a number. That number was, you guessed it, 299,792,458 meters per second. Maxwell was astounded. He'd discovered a number, a fundamental speed embedded within electricity and magnetism's laws. The remarkable part was that number matched the finest available light speed measurements. This wasn't mere coincidence, but revelation. Light, Maxwell understood, was an electromagnetic wave, a self-sustaining ripple of electric and magnetic energy, racing through emptiness at a speed determined not by chance but by the universe's very architecture. Allow that to resonate. Light speed isn't simply habit, but integrated into the equations governing reality's fabric. It's not as though the universe randomly selected that number, but more like the universe had to function this way. If electric and magnetic fields exist, and they certainly do, then light must travel at this speed. That partially answers our question. Light moves at its speed because that's the only velocity electromagnetic waves can achieve in vacuum. Anything faster or slower would violate our understood laws. But let's delve deeper. Why can't anything exceed that speed? In daily life, we're accustomed to speed being somewhat negotiable. If your automobile travels 100 kilometers per hour, it might also manage 110 if you're adventurous. With light, however, there's no enhancement, no violation, just an absolute boundary. To understand why, we must summon someone you've likely heard of, Albert Einstein. In 1905, Einstein published his special relativity theory, revolutionizing everything. One key principle of special relativity states, light speed in vacuum remains identical for all observers regardless of their motion. That might sound mild, but it's actually extraordinary. Imagine you're aboard a train moving at 90% light speed. Highly impractical but excellent for theoretical scenarios. You activate a flashlight. You might anticipate that your flashlight's beam would appear faster to someone standing on the platform. After all, the train is already moving, and you've added the flashlight beam additionally. But no, both you and the platform observer would measure that light beam's speed as exactly identical, 299,792,458 meters per second. Not marginally more, not slightly less. To make this possible, reality must contort around this principle. Time decelerates, lengths compress, mass multiplies. The universe alters its fundamental rhythm to ensure nobody, regardless of their velocity, can ever observe light accelerating. If you, a courageous astronaut, attempted to accelerate to light speed, you'd encounter a problem. As you increase speed, your mass grows, not in the excessive eating sense, but in requiring increasingly more energy for marginally greater velocity. Approaching light speed, your mass approaches infinity, meaning you'd need infinite energy to reach it. Infinite energy is quite demanding, even for the most ambitious explorer. Therefore, no matter your effort, you can approach closely, but never arrive. You can pursue light, but you'll never overtake it. This explains why light's velocity isn't merely light's velocity, but represents the universal speed ceiling, the maximum rate at which information, energy, or any massive object can traverse space. It's a barrier, a boundary, an essential component of spacetime's fabric. And here's a calming consideration. If light's speed weren't restricted to everything, would collapse. Causality, the principle that causes precede effects, would shatter. You could theoretically witness consequences before their origins, or transmit messages backward through time, creating chaos, temporal paradoxes, and severe logical complications. Instead, the universe shields us from such absurdity with this elegant velocity restriction, maintaining order, predictability, tranquility. Regardless of other changes, light speed remains constant. So when you next observe a sunset or contemplate overhead stars, remember, those light rays didn't accidentally arrive, but followed a law inscribed in physics' foundation, a law declaring this distance, no further. A limitation certainly, but one providing the universe structure, stability, and magnificence. Light doesn't accelerate because it cannot, not from weakness or indolence, but because it's flawless, exactly as designed, bound to a velocity-preserving time's forward flow, maintaining causality's integrity, and enabling our comprehension in ways otherwise impossible. And frankly, for something racing through space at nearly 300,000 kilometers per second, that's remarkably graceful pacing. Albert Einstein possessed a talent for inverting reality, while making it seem inevitable afterward, as though the universe had been murmuring secrets perpetually, and he simply became the first genuine listener. When he presented his special relativity theory in 1905, he didn't merely adjust physics regulations, but completely rewrote them. At his theory's core lay an audacious declaration: light's vacuum speed remains constant. Not approximately constant, not reasonably consistent, provided you're not moving excessively fast, but absolutely constant for everyone, everywhere, eternally. This might sound pleasant if you're drifting towards sleep, but it demolishes everything you believe about motion and time. Consider yourself aboard a spacecraft floating serenely through emptiness. You're holding a flashlight. You activate it. A light beam shoots forward at repeat, after me, 299,792,458 meters per second. Now imagine someone else, your co-pilot perhaps, is flying past you in another spacecraft at half-light speed. From their viewpoint, you and your vessel are streaking by like a blur. But when they measure that identical light beam's speed, they don't observe it moving faster or slower. They also measure exactly 299,792,458 meters per second. That's peculiar, profoundly peculiar. In the ordinary world, velocities combine. If you're walking on a moving airport walkway, your speed equals your walking pace plus the belt's speed. But with light, the walkway could be moving, the person could be moving, the flashlight could be moving, and light speed stays identical for all of them. So what's happening? Einstein's solution was beautifully disturbing. It's not light's speed that changes, but everything else. Time, space, moments, passage, objects, dimensions, all of it bends and stretches to preserve that one sacred number. Let's gently examine the consequences. First, time dilation. This one's beloved among physics students and science fiction authors alike. The faster you move, the slower time passes for you compared to someone at rest. Not just subjectively, but a real measurable phenomenon. For instance, suppose you're on a spacecraft traveling at 90% light speed. To you, everything aboard feels perfectly normal. You consume snacks, read a book, maybe wonder why you didn't pack more socks. But when you return to Earth, you might discover that considerably more time passed for everyone else than for you. Years, even decades, while you experienced a brief journey. Earth aged without you. This isn't merely theoretical speculation, we've tested it. Particles called muons created high in Earth's atmosphere by cosmic rays decay in microseconds, but when they're moving near light speed, their internal clocks decelerate, and they persist longer. Long enough to reach the surface and be detected. Time actually stretches for them as they move. Next, length contraction. This is time dilations. Strange twin. When you travel at high speeds, objects in your motion's direction appear shorter. Not through optical illusion but by physical reality. Your spacecraft would literally measure shorter along its travel path. Now, before you imagine yourself folding into an uncomfortable cube, understand that this only becomes noticeable at speeds approaching light speed. For everyday travel, cars, planes, or very enthusiastic joggers, the effect is so minute it might as well not exist. But near light speed, the universe gets squishy. Then there's simultaneity's relativity, which sounds like a tongue twister, but is actually a delightful bit of mental gymnastics. It means two events which seem simultaneous for one person might not occur simultaneously for another, if they're moving relative to each other. Imagine a train moving very rapidly. In the train's middle, a light bulb flashes. From the train passenger's perspective, the light reaches the front and back simultaneously. But from someone standing on the platform, the light reaches the train's back first because the front is moving away from the flash. Both observations are correct. Time and space are no longer universal but flexible. Local, relative, all this strangeness, time stretching, distances shrinking, simultaneity breaking down. It all occurs to protect that constant light speed. It's as if the universe examined this one number and declared everything else can bend, but this must not break. It's somewhat like a cosmic contract. In exchange for allowing light to remain constant, the universe agrees to warp everything else around it. It's a delicate balancing act, preserving causality's integrity. Speaking of causality, here's a soothing thought. This cosmic speed limit protects our sense of before and after. Because light can only travel so fast, information can only travel so fast, meaning you can't observe an event before it happens and you can't send messages into the past. Light speed limit keeps the universe logical, predictable, orderly. Without it, things would become messy. You could theoretically cause effects before their causes. You could receive messages before someone sent them. Paradoxes would accumulate, like socks in a teenager's bedroom. Instead, the universe gently says, no, let's not do that. Let's have order. Let's have a maximum speed, and let's make it sacred. And so this is where Einstein's work shines brightest. He didn't just describe light speed as a limit, but showed its reality's cornerstone, the cosmic scaffolding supporting time and space. Today, GPS satellites rely on Einstein's equations to prevent your phone from thinking you're in the middle of the ocean. Particle accelerators use them to guide subatomic particles around at astonishing speeds. Astronomers use them to decode the cosmos whispers from distant galaxies. All of it rests on this strange but constant truth. Light has a maximum speed, and that speed is identical for everyone. So next time you see a sunbeam falling through your window or a lighthouse flickering in darkness, take a moment to marvel at what that light represents. Not just energy, not just warmth, but space-time's delicate geometry itself. A quiet contract written in light's language, and no matter how fast you go, no matter how far you drift, it will always greet you at the same pace, unchanged, unwavering, and eternally punctual. So far we've explored light itself, what it is, how we measured its speed, and why the universe insists on giving it such a precise and unbreakable limit. But now let's gently pull back the camera and examine what this cosmic speed limit actually does to reality. Because once you realize that light can't go any faster than it already does, the implications are surprisingly far-reaching and in many ways quite beautiful. Let's start with something fundamental to how we understand the universe. Time. Not your kitchen clock kind of time, but the kind that ties together events, memories, and causality. Light speed limit gives time a structure. It draws boundaries around what can influence. What it reveals to the universe is you may only connect events if there's sufficient time for light to traverse between them. This concept is what physicists term the light cone. It's not a treat or a lampshade, but a method of charting which portions of space-time are linked by cause and effect. Imagine this: you're standing in a meadow, and you ignite a match. That tiny flame emits light in all directions. The farthest anything can be influenced by that match immediately, or eventually is constrained by how far light can journey from that instant forward. If someone is positioned extremely far away, say 100 light-years, they won't even realize the match was struck until 100 years later. Now reverse it. Imagine you're standing in that identical meadow awaiting something to occur. The only events that could possibly influence you presently are those whose light has had time to reach you. That's your past light cone, everything that could have possibly caused your current moment. The light cone isn't merely a clever diagram, but the boundary between possible and impossible. If something happens outside your light cone, it's not just too distant, it's too distant in time. No signal, no sound, no whisper from that event can reach you yet. It's as if it doesn't exist for you, not until the light arrives. This idea shapes our complete understanding of the universe. It means there's no such thing as instantaneous communication, no perfect synchrony across space, no omnipresent now. Instead, every moment is local. Every now is slightly different depending on where you are, and light speed is the rulebook that keeps it all consistent. Think about how this affects your view of the night sky. When you gaze up at the stars, you're not seeing them as they are, but as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years to reach us. If something dramatic happened there last week, we won't know for several more years, and that's the nearby neighborhood. Look further out, and the effect becomes even more dramatic. The light from the Andromeda galaxy takes over 2 million years to arrive. You are seeing it as it appeared when early humans were just starting to figure out how to make tools. Beyond that, we see light that departed its galaxy billions of years ago, before our sun even existed. And yet it feels so present. The stars twinkle, the galaxies glow. They seem right there, but they're not. It's history written in beams of light, traveling at their own patient pace. This delay is what allows astronomers to be time travelers of a sort. When they look into deep space, they're not just looking far, they're looking back. Every telescope is also a time machine peering into epochs long gone. And all of this insight is possible because light doesn't move instantly. Its limit gives us access to the past. There's also something elegant about how this delay enforces causality. You can't influence something unless there's time for a signal to get there. That's not just a rule, it's a safeguard. It prevents paradoxes. It's the universe's way of saying, let's keep things logical. Without this speed limit, chaos would ensue. If you could send signals faster than light, you could in theory send a message to your past self. You could say, don't eat that suspicious burrito, and if you listened in time, you'd have no reason to send the message in the first place. That's the kind of logic loop that keeps theoretical physicists up at night, and not in a good way. But with the speed of light as a cap, those loops never happen. You can't outrun your own consequences. Events happen in order. The past stays behind you, the future ahead. It's not just the flow of time, it's the structure of time, and it affects more than distant galaxies or imaginary time machines. It's built into your day-to-day life. Consider communication. When you make a phone call or send a text message, you might not think about light speed, but if you're talking to someone on the other side of the planet, there's a very slight delay, tiny but measurable. The signal is traveling as electromagnetic waves, often bouncing through satellites or fiber optic cables. These waves move at or near the speed of light, but Earth is big, and light, while fast, still takes time. Now think about spacecraft. When Mission Control sends a signal to a Mars rover, it can take anywhere from 4 to 20 minutes for the message to arrive, depending on where the two planets are in their orbits. That means, if the rover stubs its robotic toe on a Martian rock, the scientists on Earth won't know until nearly half an hour later. There's no real-time remote control. The rover has to be autonomous, making decisions on its own, because the speed of light says you're on your own out here. Even your favorite streaming service obeys this limit. Every pixel, every frame of your late-night documentary binge had to travel from some server across cables and switches, all moving as pulses of light, limited by the universe's built-in pace. It might sound like a constraint, but really, it's a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. It gives structure to space and time. It turns an endless, featureless void into a tapestry of ordered events. And, while it might seem strange to think that the fastest thing in the universe is also the thing that slows down how quickly we can know something happened, that delay, those tiny moments of waiting, are what make the universe understandable. They give us distance, perspective, a little room to think, and maybe, just maybe, a little space to rest. Let's imagine for a moment that you're not the kind of person who takes no for an answer. You've heard all about this speed limit, this cosmic traffic rule, etched into the laws of physics, and naturally, your first question is, well, what if we just ignore it? Could anything ever go faster than light? It's a tempting thought. After all, human beings have a habit of pushing limits. We've broken the sound barrier, we've sent robots to Mars, we've built machines that can smash atoms apart, so what's stopping us from finding some cosmic shortcut, something that zips along faster than 299,792,458 meters per second? Let's start with a curious little idea from the theoretical physics basement: tachyons. These hypothetical particles were dreamed up as part of certain equations, and they come with an eyebrow-raising feature. They can only travel faster than light. In fact, they can't slow down enough to reach the speed of light. That's their limit in the other direction. Sounds exciting, right? A particle that naturally ignores the speed limit, zooming through the universe like a hyperactive squirrel on espresso. There's just one small problem. No one has ever found a tachyon. Not in a lab, not in deep space, not even lurking suspiciously. In the gaps between equations, they're like a rumor in a small town. Always mentioned, never seen. And even if tachyons did exist, they would cause more problems than they solve. If you could use them to send information, you could violate causality. Meaning, you could send a message into your own past, and if you've ever watched a time travel movie, you know how messy that can get. Grandparents disappear, timelines collapse, and everything starts to unravel. So theoretical physicists mostly agree, tachyons are fun to think about, but probably not real. They belong in the box labeled interesting, but nope. But what about other fast things? Let's look at quantum entanglement, one of the spookiest phenomena in all of physics. When two particles are entangled, measuring one seems to instantly affect the other, no matter how far apart they are. You measure one here on Earth, and its twin on the other side of the galaxy reacts in perfect sync. It feels like a cosmic cheat code. Surely this is faster than light. Well, yes and no. The key point is that while entanglement correlations appear, instantly they don't transmit usable information. There's no way to control the outcome of the measurement on one particle, so there's no way to use it to send a message. It's like two people flipping identical coins across the universe, and somehow, always getting matching results, but neither one can use it to say hello. Einstein himself was deeply bothered by this. He called it spooky action at a distance, but modern experiments have confirmed that entanglement is real, and that it doesn't allow for faster-than-light communication. The universe is spooky, yes, but still respectful of the speed limit. Then there's Cherenkov radiation, a bit of glowing weirdness that happens when a charged particle travels through a medium. Like water faster than light, can traverse that identical medium. Yes, you heard correctly. Light doesn't always move at its maximum velocity. In materials like glass, water, or plastic, it decelerates slightly due to interactions with atoms. So if a particle moves faster than that reduced velocity, it creates a kind of light shockwave similar to a sonic boom. This is what causes the eerie blue glow you observe in nuclear reactors submerged in water. It's not that anything is violating the universal speed limit, just the local speed limit inside the material. Light in a vacuum still reigns supreme. No actual laws are broken, just bent a little in the pool. But what about going the extra mile? Could we construct a warp drive like in those classic science fiction shows? Could we bend space itself instead of just moving through it? Well, in theory, perhaps. One idea proposed in the 1990s by physicist Miguel Alcubierre suggested that it might be possible to contract space in front of a spacecraft and expand it behind. This would let the ship ride a wave of warped spacetime, technically never moving through space faster than light, but still arriving at its destination quicker than a beam of light could on its own. It's a clever workaround, but it comes with a few complications. First, it would require a substance with negative energy density, a kind of exotic matter that we have no evidence for, and no real idea how to create. Second, even if you could build such a thing, the energy requirements would be, well, let's just say planet-sized. Some calculations suggest you'd need the mass energy of Jupiter just to move a grapefruit. So for now, warp drives remain firmly in the realm of imagination. Cool. For storytelling, tricky. For engineering, there's also the idea of warp tunnels through space-time that could, in theory, connect to distant points instantly. Think of them as cosmic shortcuts or space-folding bridges. Again, the math allows for them, but again the problems stack up. Stability, exotic matter, time, paradoxes. It's like trying to build a suspension bridge using soap bubbles and hope. And even if you could make one work, it wouldn't technically be faster than light travel. You'd just be taking a shorter path. The light still wins the marathon, but you found a convenient side street. So where does that leave us? Despite the clever ideas and curious exceptions, nothing with mass or information has ever been observed traveling faster than light. Every time we think we've found a loophole, the universe calmly steps in and closes it with a raised eyebrow and a chalkboard full of equations. And maybe that's not such a bad thing. The speed of light might seem like an irritating restriction, like a locked door at the edge of possibility. But in reality, it's more like a safety rail keeping the universe from falling into paradox chaos. And spaghetti timelines, it gives us structure, it gives us order, and it gives us a kind of cosmic serenity. Knowing that no matter how weird things get, there are still boundaries that even the universe won't cross. So if you ever find yourself wishing you could beam across the stars, or message your past self about tomorrow's weather, take comfort in the fact that light itself, swift, silent, and steady, is moving as fast as anything can. It's already leading the way, and perhaps that's enough. By now you might be sensing a pattern. The speed of light isn't just some arbitrary number. It's a cosmic foundation stone woven into the universe's very architecture. But what if it's telling us something even deeper than we realize? What if that mysterious, almost poetic number 299,792,458 meters per second isn't just a limit on speed, but a key to understanding space-time and reality itself? Let's take a relaxed stroll into one of the more philosophical corners of physics. Don't worry, we're keeping it cozy, you can keep your slippers on. One of the most intriguing ideas in modern physics is that the speed of light is not just the pace of a photon, but a kind of conversion factor, a bridge between space and time. That number, let's just call it c for convenience, is what lets us translate distance into time and back again. It's like the universe's built-in translator. You've probably seen this in Einstein's famous equation, E equals mc squared. Here the speed of light appears as a bridge between mass and energy. It tells us how much energy is locked up inside a certain amount of mass. But c also shows up all over relativity in equations that describe time dilation, length, contraction, and space-time curvature. The fact that it keeps popping up is no coincidence. It's a hint that c is more than just a speed. It's a kind of universal glue. Let's explore that with a simple calming thought experiment. Imagine the universe is like a great woven fabric made up of both space and time, not two separate threads, but one single material space-time. This concept, while sounding like a science fiction buzzword, is very real in Einstein's theory. Space and time aren't separate dimensions, they're interlinked, and they behave like one smooth, flexible thing. When you move through space, you're also moving through time. When you speed up, time slows down. When gravity pulls, it bends both space and time around it. But here's where the speed of light comes in. It's the conversion rate between space and time. Think of it like the exchange rate at a currency desk, but instead of euros and dollars, it's meters and seconds. This helps explain why you can measure distances in light years. That's not a measure of time, it's a measure of distance. 1 light year is how far light travels in 1 year. The fact that we can use a time-based unit to describe distance speaks to how deeply interwoven the two concepts are. So when we say nothing can go faster than light, we're also saying nothing can mess with the relationship between space and time. The speed of light defines that relationship. It's the stitching that holds the whole quilt of reality together. There's a certain calmness in that, because it means the universe has a kind of built-in consistency. No matter where you are, no matter how fast you're moving, c remains the same. It's a cosmic constant that makes equations work, keeps cause ahead of effect, and ensures that physics behaves itself, even at the edges of black holes or the hearts of galaxies. In fact, physicists don't even treat c as just a speed anymore. In many natural units used in theoretical physics, they actually set the speed of light to just the number 1, not because they're lazy, but because it simplifies things. Once you do that, space and time can be treated on equal footing. Distances and durations can be measured in the same units. The equations get cleaner, more elegant. It's like the universe tidies itself up. This leads us to an even more curious idea. Maybe the universe isn't built for light to move. It's built around the speed of light itself. Think of it like this. When light travels, it doesn't experience time. From the perspective of a photon, the moment it is emitted and the moment it's absorbed happen at the same instant. There is no ticking clock inside a beam of light. Time from light's point of view simply doesn't pass. That's a wild idea, but it's backed up by relativity. The faster you go, the slower your clock ticks. For something moving at the speed of light, the ticking stops altogether. It exists only in motion, in the act of moving. It's never at rest. In fact, it can't be. And this brings us back to that poetic truth. Light is not just traveling through the universe, it defines the structure of the universe as it goes. The speed of light is not something that light chooses, it's something the universe insists upon. Even the way we define our basic units of measurement now revolves around this speed. Since the year 1983, the meter has been defined based on how far light travels in a certain amount of time. Specifically, 1 meter is the distance light travels in 1/299,792,458 of a second. That's not just poetic, that's precise. We've made the speed of light the ruler against which all rulers are measured. It's our measuring stick for both time and space, and perhaps that's the most grounding part of all this. In a universe that can seem vast and strange, filled with dark matter and quantum uncertainty, there is something beautifully fixed. The speed of light is a constant you can build your world around, because we quite literally do. So next time you see that little flicker from a candle or the soft starlight filtering through your window, know this. You're witnessing more than just brightness. You're seeing a cosmic law in action, a message from the very geometry of space-time. A reminder that while the universe may be immense and mysterious, it is also quietly, elegantly consistent. Light doesn't just illuminate the world. The speed of light sets the rhythm of the cosmos, and perhaps on a quiet night, as photons from distant stars drift gently down onto your face, you can imagine the universe whispering in its own language softly, steadily, at exactly 299,792,458 meters per second. This isn't just some footnote in physics textbooks. It's the pulse of the cosmos, the stitch in the fabric of space and time, and the steady metronome that keeps reality in rhythm. woven into your everyday life in ways that might surprise you. Every time you tap your phone screen, stream a video, or send a sleepy emoji to a friend, you're harnessing the power of light, traveling through fiber optic cables, slender strands of glass, stretching beneath oceans and continents, forming a global web that carries information at nearly the speed of light, with tiny flashes representing ones and zeros making their journey through cables and bouncing through routers to arrive at your screen. These same principles guide GPS satellites orbiting Earth, each sending signals with timestamps down to the nanosecond. You'll receive comparing arrival times to triangulate your location while accounting for both special and general relativity. Satellites' clocks ticking slower due to their speed and faster due to reduced gravity. Corrections that prevent your GPS from being wrong by several kilometers every single day. Vision itself relies on light's behavior as photons bounce off objects and enter your eyes, traveling through cornea and lens to focus on your retina, triggering chemical changes in rods and cones that your brain reconstructs into vivid, colorful images of trees, sunsets, and oddly judgmental houseplants, with depth and motion perception depending on the tiny delays between light reaching each eye. Refraction, the way light slows and changes direction when entering different materials, makes straws look bent in water, creates shimmering effects on hot roads, and enables the function of eyeglasses, microscopes, telescopes, and camera lenses, while microwave ovens use lower frequency electromagnetic waves to make water molecules jiggle and heat your food. Radio stations, television broadcasts, Wi-Fi signals, and Bluetooth connections are all forms of electromagnetic radiation zipping through space at light speed, following the same rules that govern starlight and lasers. While X-rays pass through soft tissue to reveal bones, and MRI machines use electromagnetic fields to create detailed body images, everything we know about the universe beyond our solar system has been delivered by light. Telescopes capturing faint photons that have traveled billions of years across space, carrying encoded stories about galaxies, nebulae, and black holes that we decipher by analyzing color, intensity, and spectrum, with wavelength shifts revealing galactic motion and brightness dips hinting at planetary transits. The cosmic microwave background represents the oldest light in the universe, traveling undisturbed for nearly 14 billion years, a faint, uniform glow that fills everything, the cooled remnant of when the universe became transparent about 380,000 years after the Big Bang, when neutral hydrogen formed and photons could finally roam free through what was once a dense, opaque fog. Photosynthesis begins when sunlight hits leaves, photons striking chlorophyll molecules and exciting electrons in cascading reactions that store energy in chemical bonds, fueling the growth of plants that feed animals in an unbroken chain of life, making every meal you've ever eaten start with a photon from the sun. Your circadian rhythm responds to light changes throughout the day. Morning light telling your brain to stop producing melatonin, while evening's fading light allows it to rise again, your body constantly tracking ambient light and adjusting its rhythms to sync with the world's subtle cues. Light connects everything, not just eyes to objects or stars to telescopes, but moments to each other, serving as the universe's language with different wavelengths telling different stories, some revealing the chemical composition of distant galaxies, others warning of gamma-ray bursts, some carrying infrared warmth from newly formed stars, others painting rainbows across oil slicks and soap bubbles. Take a moment to imagine a single beam of light drifting through vast emptiness. No planets, number stars, no gravity, just one solitary photon gliding effortlessly through vacuum, neither speeding up nor slowing down, having no mass, no rest, and no need for fuel, simply existing in motion at the only speed it knows, participating in the great cosmic symphony, a dance of information, energy, and time that weaves the structure of everything we know, quietly working behind the scenes in nearly every area of modern life as the silent engine of the everyday, racing around, through and within your world at exactly 299,792,458 meters per second. The hidden geometry of interference and refraction reveals light's true power. It doesn't just show us what's there, it tells us how things work, with split beams passed through prisms, revealing that white light is a symphony of colors. Light from supernovas carrying fingerprints of heavy elements forged in violent furnaces of dying stars, and our instruments learning to listen better with radio telescopes, hearing whispers of hydrogen clouds, X-ray telescopes, seeing skeletons of galaxy clusters, infrared instruments peering through dust to watch stars being born, and gravitational wave detectors tuned not to light but to ripples in spacetime itself, another cosmic messenger, complementing what photons have always told us. All of this paints a picture of a universe, not as a cold, silent expanse, but as a place full of signals, full of stories, full of light, reminding us that we're not separate from the cosmos, observing from afar, but bathed in it, shaped by it, part of it. The atoms in your body forged in stars that lit up billions of years ago, their light crossing interstellar space, touching gas clouds, seeding new solar systems in the same process that created the carbon in your cells, the calcium in your bones, the iron in your blood, making you quite literally star stuff carried to you by light. This restless traveler, this photon with no mass, no clock, and no home, does more than move it, connects the ancient past to the present moment, ties atoms to galaxies, lets eyes see and minds understand, serving as a constant companion in a universe so vast and full of unknowns, not just fast, not just fundamental, but familiar. The quiet presence that turns space into story, fills the dark with meaning, and whispers across the emptiness, I am still here. Tonight, as you settle in and let your thoughts drift with the stars, remember that even in the quiet, even in the dark, light is always on its way. And so here we are, gently floating back to where we began, having set out to answer a simple question about why light has a speed limit. Wandering through fields of photons and dancing with electromagnetic waves, listening to cosmic whispers, watching time bend and space stretch, observing clocks slow down and stars speak in ancient beams, traveling through cables and galaxies, through your phone, your eyes, and the quiet glow of the microwave background. The answer, in the end, is as elegant as it is profound. Light travels the way it does because the universe is built to let it, and to be shaped by it. Its speed not just fast, but fundamental, a cosmic rule holding everything together from the pulse of atoms to the stretch of galaxies, something that cannot be broken or outpaced. And perhaps that's a good thing. The speed of light gives us order, gives us time, gives us a way to understand, gives us stories and sunsets and the warmth of starlight on a cold night. So maybe we don't need it to be faster. Maybe it's already perfect, just the way it is. Now, as we bring this quiet journey to a close, let me ask you again, where in the world are you listening from tonight, and what time is it right now wherever you are? Curled up in bed with stars outside your window, or sitting quietly on the other side of the world with morning light just beginning to rise. Thank you for spending this time with me, and if this helped you wind down or sparked a quiet wonder, I'd be truly grateful if you gave it a like and tapped subscribe to help others find their way to this calm little corner of curiosity. And if this kept you awake, well, at least you might have learned something interesting while waiting for sleep to find you. Until next time, rest well, and may your dreams move at just the right speed.